Hello, hello. Can you hear me? Yeah, thank you. Okay, so welcome back. So before starting the second lecture, I would like to make some ratification from stuff that I said yesterday. So first one is that Siva brought to my attention yesterday that actually the story that I told you about the vitros of medieval cathedrals in Europe like flowing actually is not true. So actually this is very, very funny because, you know, that's something that we are taught when we study physics in statistical mechanics. That's like the traditional example of glasses. And, but actually, apparently if you compute the difference of energy in the potential, the time scale that you take for actually to flow, so it actually flows, but the time scale that it flows is beyond any kind of human time scales. I think apparently in the article that Siva sent me yesterday, it's like 1 billion years. So yeah, so it flows, but it flows very slowly. And apparently, like, I think this misunderstanding comes from the fact that, you know, if you look at the cathedral, like glasses indeed, like sometimes the bottom part of the glasses are thicker. And apparently these are like defects of fabrication because, you know, medieval times people didn't know how to produce perfect glasses. So that's what I read after. But yeah, it's kind of something we are told we are told in physics, but it's not true. So yeah, thanks Siva for bringing this up and demystifying this. I mean, you know, I've taught this so many times, and that's the first time someone brings me. So that's great. The second thing I wanted to say is that I went a bit too fast, and last time we were starting to look at some optimization problems, and in particular, I motivated the introduction with this quadratic problem, which is like to minimize this quadratic form. And then I was saying that, you know, depending on the constraint set, whether it was convex or not, the problem can be hard or easy. But actually, I forgot to mention that actually J needs to be PSD for it to be easy. It's like what I mean by easy is that the problem can be solved with a polytime algorithm efficiently, even in the worst case. So it's true that when this guy is not PSD, you can find some problems for which this is also NP hard, even when the constraint set is convex. So yeah. And also I made this comment, like I went fast and I said, like, you know, if you take the sphere, then that's the operator norm of J, which is a case where you can efficiently compute. Of course, like the convex set is actually the unit ball, but then the extremizer, when this is going to be in the boundary, and then that's the operator norm. So just to be precise. Okay, so last time we stopped by introducing the key object that we are going to be studying in this lecture, which is what we call the Boltzmann-Gibbs distribution. So that's a probability distribution, or probability density, depending on the configuration space. But in the case that we're going to be studying today, the configuration space is going to be discrete. So this is actually just a probability distribution on this discrete space. And it's a distribution that is actually parameterized by this, like what we would call in machine learning, like an energy-based model. So you give me energy, this energy weights configurations, and then the probability of a given configuration is given by this exponential of minus beta times the energy of the configuration. So configurations that have different energy are going to have different weights in this measure, and depending on beta, you put more or less weight on configurations of low energy. So for instance, when beta is equals to 0, which we call the high temperature regime, this is like the uniform measure over the configuration space, while when beta is infinity, this measure is going to be peaked. And also I had some questions about what I mean by peaked. Essentially, you can think this and you can formalize everything. This is going to be like just like a point measure at the minimizers of the Hamiltonian, of the energy function. So just going to converge to Dirac masses on the minimizers. And since this measure is not log concave, you can have like several minimizers. It depends on the energy function that you give me. And actually, we're going to be interested in cases exactly where this is not log concave. Otherwise, probably would not be needing all this machinery from statistical physics. Okay, so that's where we left last time. And most of today's lecture, and I guess in the full today lecture, is going to be focused on studying one particular case of this problem where we can solve everything. So we can explicitly write everything. And and where you can see much of the phenomenology that I described yesterday in the historical introduction between the connections of statistical physics and machine learning. So yeah, so I think that this is going to be a bit far, let's say, from some problem that you might be interested, but here is where you can understand everything. So bear with me, try to make sense of what I'm going to do this in this lecture, and then when we go towards a problem that looks more concretely like a problem that you have faced in machine learning or in TCS, the ideas are going to be the same. It's just that the computations are going to be much harder. So let's study this with care. Even though it might seem like a simple problem, it's very instructive. Okay, so let me define the problem. So we're going to be studying this high dimensional probability measure. So forgot to put here the dependency on the dimension D. So the Hamiltonian, so I give you the Hamiltonian, this defines the measure. So the Hamiltonian for this model is going to be this very simple function. And my configuration space is going to be the hypercube. So my spins actually, my degrees of freedoms are actually spins, which are just binary variables in the hypercube. Okay, so this can be seen as like a slightly version of this problem that we introduced last time, where this matrix J is the all-one matrix. And so, everybody speaks to everyone. So for example, like I said, that you can think, for example, with this problem, like when J is the adjacency matrix of a graph, and then this is like a two-body interaction where spins which are connected in the graph interact. So this problem can be seen as just having like, a fully connected graph where, let's say, everybody speaks with everybody. So everybody interacts with everybody. I guess I didn't miss any. Or so can like say have I, J, and then you have like interactions in this complete graph. And note that there are two competing terms. So remark two competing terms. So there is one term which in physics we would call like the interaction term, which is the term that couples the degrees of freedom, couples the spins. And since we want to minimize the energy, we want to make this term as big as possible because there is this minus sign here. So this is as big as possible when the spins are aligned. So this term favors alignment. So if all Si is equals to Sj, then this is maximized, so they can be all up or all down. So, configurations which are like this or the other way around. And then you have the second term, which is the term minus H I 1 to the Si. And so this term favors alignment with sign of H. So I forgot to mention, but H is just a real number, okay? So it can be positive or negative. And if H is positive, this term is going to be maximized when these have the same sign as H, and otherwise you're going to flip the sign and then you're going to pay a price because you want to minimize the energy. Okay? So that's the first thing. So there you have a competition between two things, like all spins want to align with their neighbors, and everybody speaks to everyone, but the spins also want to align with the field. So by the way, H, the parameter H is what we call external field. And the language here comes because, so this model was originally introduced by Pierre Weiss, so they were studying, so actually Curie and Weiss. Actually, I think the model was first introduced by Curie. So Curie wanted to study the phenomenon of ferromagnetism. So the ferromagnetism is the phenomenon where you have, like, let's say, a magnet, and then you hit the magnet, and then you lose magnetism. So you have something that is magnetic, and then if you hit it up, you lose magnetism. So there is this transition between what we call a ferromagnetic state, where the magnet actually has magnetic properties, and what we call a paramagnetic state, where it loses the magnetic properties. So it just becomes like, I don't know, paper. It's paramagnetic, it doesn't attract when you bring a magnet close by. And I think Weiss was the first one to study the model. So I think Curie was actually observing this phenomenon experimentally, and I think, if I'm not mistaken, Weiss was the first one to introduce the model to model this phenomenology. Okay, so you can think about the spins as being like units of magnetism. So if they're pointing up, let's say they are attracting each other, and otherwise they are repelling. And this like says that they want all to be like in a magnetic state, and what we call H here is an external field in the language of physics, because if you put a magnetic field and you put a magnet inside a magnetic field, the magnet will tend to align with the field. So this is kind of modeling the effect of experimentally in a lab trying to force the magnet to align with an external field. So we call H an external field. So I'm going to talk about field, but it's just a constant H. Okay, so the second thing that is important about this model, so that's the remark A. Remark B is that each spin, so each SI only feels its neighbors through their average. So if you look at the energy function and you say I want to marginalize one spin, so let's say I take spin SI for any I between the D spins, what I obtain is something like J different from I, so Sj minus H Sj, J different from I, and then I need to put back what I removed, so there is a 1 over 2D Si squared, so that's the diagonal. This is always 1, so that's the constant, and then minus HSI. So from here, you realize that actually the spin Si only is going to interact with the neighbors through this average field, or through the sum, like the mean magnetization. So this is the sum over all the other spins minus the I. So we call this like kind of a mean field. Okay, that's the average field. And that's going to be very important from what follows. And the third comment, C, is that every interaction between the spins, so interaction between spins, between individual spins, which look like this. So if I just take, let's say, S1 and S2, that's how the way they feel each other, they interact. So this is of order 1 over D. So if the dimension is large, so if I have a system with many, many, many spins, essentially, every interaction is very small. And the fact that they interact through the average is going to be something, so the average, including the D here, maybe I should, put the D there inside the definition of this guy. So the average is going to be order 1 quantity, while each singular interaction is going to be order 1 over D. So they are weakly interacting, but when you consider the mean interaction, so you consider the mean field, they actually interact in a way which is meaningful when D is large, okay? So for now, everything like all the O's and theta's I'm going to write with respect to D. So any comments or question about that? Yeah?
You're missing a term at the beginning.
Where? In the definition of the Hamiltonian? Third board? Here? Yeah, thanks. Yeah, so yeah, for the double sum. Is that all? Yeah, that's.
The whole thing is lower, and then each term should be divided by t because
so each term should be, so this should sum over I. So this is the field, so that's good.
then the third term should.
Yeah, the third term as well. Yeah. Yeah. Wait. No, because I'm discriminating one I, so that so I'm just. Oh yeah, yes. So here I have like all the terms on the magnetic field, and I'm just taking one. So when you put this back here, this is sum over all of them. So this one, I think this one has no sum, right?
Third term.
The third term. So this term. Yeah. Yeah. Okay. Yeah. Okay. Let me be consistent then and just sum. Yeah. Thanks. Yeah, that's the diagonal term. Thank you. Yeah, keep correcting me because I often make this type of mistakes in the board. So, I also sometimes say something and write something different. So whenever I do that, please shout out. Okay, so the comments B and C together is what we call a mean field model. Okay, so whenever you hear people talking about mean field, you can take mean field. You know, it's not a very well-defined concept. People use it in different ways, but one way of understanding, like at least for this model, is that it means that everybody talks to everybody, and the interactions between individual degrees of freedom are small. They only matter when you take collective. So, you know, macroscopic or statistical averages between degrees of freedom. So B plus C is roughly what we call in physics a mean field model. And I guess the name is quite natural from this perspective because of comment B. Okay, so what we're going to be interested, as I said, is like to study the Boltzmann-Gibbs distribution for this model. And so now let's discuss the way that this measure behaves when D is large. So high dimensional asymptotics. Try to keep the same division. Okay, so the idea is very simple, and the idea essentially relies on comment B, which is going to be, okay, since the Hamiltonian only depend on this average interaction between the spins, let's try to write what is the probability of the average interaction being something. So let's define. So define what we call the magnetization in physics. So S bar D equals to 1 over D sum over I from 1 to D of Si. And so this is essentially the average over the spins, and we call this the magnetization. It's going to tell us how much the system is magnetized up or down, right? If the mean magnetization is positive, then it's magnetized on average up. If it is negative, it's down. So it describes like some kind of a summary statistics of the system. It summarizes like macroscopic behaviors of the system. Also, if you think about in mathematical terms, like this kind of aggregate of microscopic variables tends to concentrate, right? It's the mean. So the mean has good concentration properties. And that's always going to be the case in this type of like statistical physics approach. We are always going to be looking for quantities which concentrate when the dimensions are large. Okay, so by the way, note that this is a discrete variable and it can take values on the set of -1, -1 plus 2 to the D, up to 1 minus 2 to the D, and plus 1. Okay, so now we can write the Hamiltonian. We can write as the following. So let's look at the Hamiltonian. So we have this double sum. So we want to write this double sum in terms of the average magnetization. So that's quite easy. So you just need to be careful with your factors of D, but you can note that essentially can rewrite the Hamiltonian in this way. Right, so that the term of the field, we just need to divide and multiply by D. That's easy. There we need to actually write this double sum as the square of a single sum. But then we realize that we need to divide by D. But since there is this square, there is a D squared, and the D square, we need to account for one extra D that we are missing. And so the whole thing is proportional to D. So that's nice because we expect in physics usually the energy of the system to scale proportionally with the dimension of the system. So that's reassuring that we will obtain something which is proportional to the dimension. And that's actually the right scaling. For the problem. Okay, so once we realize that the system only depends on the average magnetization, it's very natural now to try to write a measure that is not over the configurations, but a measure over the average magnetization. So let's do that. So the probability that S bar D equals to some magnetization M. So I just need to have my weight factor, partition function. Then I have the energy, which is the exponential over beta. And then I just essentially have this, 1/2 m squared plus h m. And then, okay, what do I need to include is that I need to include the counting of how many ways do I have to pick a configuration that have a given magnetization, right? And that's just a combinatorial factor. It's essentially D choose D n plus 1 over 2. So you can convince yourself that actually this just counts how many ways I have to pick a given magnetization. So it's very easy, like let's say if you have all ones, there's only one way of having all ones. That should be 1. So if you have -1 and the rest +1, there is D ways of placing this -1 among the +1s. So this should be D, and so on. And that's just combinatorics. And that's a very nice thing because it's also, again, something that is going to appear over and over in the computations in statistical physics, which is the fact that once we identify the macroscopic quantity or the summary statistics that we want to study, that also is going to be like the order parameter of the system, and we can write the energy as a function of the summary statistics, then there's always going to be a counting term, which we call like the entropic term, which counts how many ways the system has to microscopically organize to obtain a given configuration with that summary statistics. So if you can see this as an energy, and that's quite obvious why, because comes from the Hamiltonian, and you can see this as an entropy term. And this entropy term comes from the fact that I'm rewriting now the measure on this space of the summary statistics of this macroscopic quantity. Now, once we did this, I think it's quite clear what one needs to do. Now you just need to take the limit, because in the limit, essentially, I can, these things are going to stay where they are. Oh, by the way, sorry, I forgot a very important factor, which is a d here, right? Everything here is proportional to d. So that's going to be an exponential of something which is order 1, because these averages are order 1, times d. So this exponential is going to be very large proportionally to d. But I have this entropy term, and this entropy term I can use Stirling's approximation. When d is large, I can exponentiate it, use Stirling's approximation, and this is going to give a contribution which is also proportional to d. So these two terms are really of the same order, and they're really competing between trying to minimize the energy and try to maximize the entropy. So these are really like a fight between these two terms. And so this I can write in terms of a proposition, which is, so for any positive beta, the limit when d goes to infinity of the logarithm 1 over d of the logarithm of this distribution over the summary statistics going to be given by this. So let me just write and then I will explain. Okay, where and Sm, I need to define Sm, that's minus 1 minus m over 2 log minus m over 2 minus 1 plus m over 2 log 1 plus m over 2. Okay, so there is one more thing I need to define. So I need to define m star. M star is going to be one of the argmax of this potential, where m minus 1. Okay, so let me try to unpack a little bit this, and then we can discuss what this tells us about the problem. So, okay, we are saying that, okay, when d is large, so what I was saying is that all these things scale as an exponential of d, right? I claim that, okay, this is pretty obvious, the energy is pretty obvious, but the entropy, if you use Stirling's approximation, I claim that you can write this as exponential of d times something, okay? Plus some corrections in d. So it's quite natural that I'm going to look at the logarithm of this, and I'm going to divide by d. So this whole thing should be an order 1 quantity. Okay, should concentrate when d is large. All this whole thing should be like something which is like a number. And this number is parameterized by the difference between two potentials. So between a potential evaluated at two values. So this potential phi. This potential phi is given by the sum over two parts. So the first part is the energetic part. So that comes directly from here, right? Beta times m squared plus hm. So that's pretty obvious. And then there is this term. This term is exactly the term, the leading order term in the Stirling approximation of this entropic factor. So that you can check. And what we call like the entropy. And it's not very surprising that actually this is just like the binary entropy. It's like something that appears everywhere in combinatorics, like when you expand this type of counting factors. So it's just given by this 1 minus m over 2 log plus 1 plus m log of the same thing. And the difference is between the probability of this being m and the potential evaluated at the maximizer of this potential, which means that, you know, the probability, this essentially is telling us, so in a hand wave way, this is telling us that P of S bar of D being equals to M. So the probability that the system has magnetization M is approximately, when D is large, as the exponential of D times this difference, this phi of M minus phi of M star. Okay, so this is essentially telling us that, minus, and wait, not minus, plus, because essentially this is the maximizer. So since this is the maximizer, this difference is negative. So the probability is going to be very, very, very small, exponentially small in D, if you move away from this value. Essentially, it's telling us that the system, when D is large, is essentially having, with high probability, magnetization M star. And M star is the extremizer of this potential function. So for those of you who know, this is called a large deviation principle. So if you know, you know. If you don't know, that's what it is. In high dimensional probability, whenever we have something that the probability is exponentially small in the deviation parameterized by a potential, that's called a rate function in large deviation theory. That's what we call a large deviation principle. And there is a whole literature in high dimensional probability about this. So essentially it's telling us that the system, it's really, really, really going towards one magnetization, which is this M star. And this M star is given by solving a low dimensional optimization problem. You just need to find the maximizer of this potential. And that's quite remarkable, right? Because think about it, like if I tell you, if I give you this Boltzmann-Gibbs distribution and I tell you, hey, just like a sample from it, it's hard. It's a high dimensional probability distribution. It's not log concave. How do you do it? Try to sit down, open a Python Jupyter notebook, and try to sample from this measure when D is large. It's hard. Try to do whatever method you like, you know, Markov chain Monte Carlo and whatever. You're going to see that it's not obvious how to sample from this measure. I'm telling you that actually it's very simple when D is large because essentially the system is behaving in a very simple way, and this simple way is just like boils down to solving a one-dimensional problem, which you can just solve by line search on your computer, right? This is you can very efficiently solve this low-dimensional problem. So I'm reducing this high-dimensional problem to a low-dimensional problem, high-dimensional optimization problem, if you want, or sampling problem, the low-dimensional optimization problem, which is very simple to solve. And that's going to be a recurrent thing in statistical physics of disordered systems, is that we are going to start with a very hard high-dimensional problem because the problem is mean-field, because the problem has these properties that, like the degrees of freedom interact in a certain way, which only depend through some summary statistics, the problem can effectively be written as an effective problem in the space of the summary statistics, which here is the space of M. And here is only one variable. And so you just have a potential of one variable. When you do machine learning, sometimes you're going to have 6 variables. So it's not so easy to study this potential because it's going to be a 6-dimensional potential. It's still low dimensional, but 6-dimensional potential. Here is very simple because it's one variable. And yeah.
Like the S bar
Yeah.
is going to kind of converge to M star, right? So does that tell us like about the original S
Yeah.
as well? Or?
Can I come back to that in 15 minutes? I'm going to get exactly there, like how actually to sample from the high dimensional measure using the mean field result. But I'm going to get there. And if you're not satisfied, you can ask again like in a couple of minutes. Okay, so by the way, here we did something. We derived this large deviation principle for the measure, but equivalently, I could have written everything down in terms of what we call the free energy density, or in this case, it's going to be a free entropy density. But you know, since we are among mathematicians, I'm not going to make too much the difference. It's just a question of minus sign. So it's not going to be very important, but you know, physicists are very picky about that if you make confusion between entropy and energy. So moreover, minus beta f beta h, this is what I'm going to call the f is what I'm going to be calling the free energy density, which I'm going to define as the limit 1 over d when d is large of the log, not of the measure, but of the partition function. So this thing can also be written in terms of the maximum over this m in the interval of phi beta h, which, as I defined before, is just phi of beta h m star. So actually the value of the potential at the extremizer gives me what I call this free energy density. And my point here, the reason why I'm introducing this at this point is that most of physicists, they would not talk about the large deviation principle. They would not talk directly about the result on the measure. They would talk about the result of this quantity. They would straight away start the problem. If you open a physics paper, we're going to study the asymptotic limit of the free energy density. And then they would derive a result for the free energy density and eventually never talk about the large deviation principle. But you can see that the potential is the same. And this is also something that is always the case, is that whenever you derive a result for the free energy density, you can translate this result in terms of a large deviation principle for the measure over the summary statistics, okay? So these things are completely equivalent pictures, whether you study the log of the partition function or whether you study this measure, okay? So just most of the time physicists will care about this. I guess mathematicians will typically care about this. It's just a question of culture. Okay, so I think I'm not gonna give you the proof of this, but I can, in the notes that I wrote, by the way, I forgot to mention there are notes for this course. So almost everything I'm saying here are in the notes. So in the notes, there is a guided exercise of how to derive this result. And it's not very hard actually to derive it like, rigorously. Essentially, you just need to derive some upper and lower bound for this measure. And it's very easy. Like essentially you need to do the Stirling approximation. And then using the Stirling approximation, you can derive almost straightforwardly I think the upper bound. And then the lower bound, you need to work a little bit, but it is essentially the same thing. Up to a factor 1 over d plus 1, the lower and upper bound match. And so when d is large, you get the quality. Okay? Are there any questions about the result? Because otherwise, I'm going to discuss Cynthia's question. and then we're going to talk about phase transitions. Yeah? The goal here is to minimize h of s. So it depends, actually, the question. I could have introduced this problem in a completely, like, say, mathematical way. We want to minimize like h of s. Let's solve this problem. This is a non-convex problem because the constraint set is discrete. And so, okay, let's solve this non-convex problem using physics. That could be a well-defined motivation. And then if this is the case, what I'm going to be interested in is the beta large limit of this quantity, right? Fine. However, this problem was not introduced this way, right? Like, this problem was introduced because in the usual chain of thought of physics, right, which is you start with a experimental observation, which is, hey, if I get a magnet and I heat it up, it loses magnetism. What is going on? And then if I cool down, the magnetism doesn't come back. That's weird. What is going on? Someone comes and say, look, your material is too complicated. There are too many atoms of different types. Each magnet has a different crystalline structure. Like, let's just model this very simple energy function where each atom has a unit of magnetism, which I call spin, up or down. And then I'm going to write the Boltzmann-Gibbs distribution for this problem. And by the way, the reason why we write the Boltzmann-Gibbs distribution in physics is because this is the, like, if you write Langevin dynamics, it's going to converge, right? Any kind of a, let's say, any kind of a physical dynamics which is local and satisfies physical properties such as detail balance is going to converge to this measure. So that's why people study these measures, because it is the limit, what we call the equilibrium measure of physical dynamics. So that's why people are interested in this measure. And they say, let's study this measure for this problem. And they observe that here, as we're going to see maybe in 15 minutes, this problem describes exactly this transition in beta. So actually, the interesting thing for us here in what comes is not the beta equals to infinity limit. It's actually going to be what happens as you vary beta from being low to high, or from the temperature from being high to low. And then how does this potential describes the physics of the measure? Yeah. Beta corresponds to the inverse temperature, 1 over T. It's literally the temperature. It's literally like the AC, right? You turn on and off in your hotel, like, you know, it's literally that, like. Yeah. Exactly. So if you want to think about the physical problem, I have this piece of a magnet, like, you know, you take the magnet from your fridge, you put on the stove, and then you turn on the stove, and you increase the temperature, and you're going to see that above a certain temperature, if you take the magnet out, let it cool down so you don't get burned, and try to see if it's still magnetic, you're going to see that it's gone. And then if you cool it down, even if you cool it down, even if you put it in the fridge, it doesn't come back. So that's the experimental setup if you want. And actually something that you can do. It's fun. Like, you can actually check that this is if you take a magnet, like a fridge magnet, and you heat it up in the stove, the magnetism is gone and then it doesn't come back. At that temperature, yeah. Yeah, and then I often get this question, and this is something that we learn in physics, is that why the Boltzmann-Gibbs distribution? So from a probabilistic point of view, you can say, okay, as long as everything is well defined, I can always consider this, I can always parameterize the distribution in this way. So, you know, there's nothing special, but like this type of distribution with an energy function is interesting because if you consider physical dynamics, as I was saying, like by physical dynamics, I mean the process in which the molecules and atoms and of your system are gonna change as, for example, you change the temperature. You know, it's gonna take some time from them to reach an equilibrium state. And this process of reaching equilibrium, that's what I mean by physical dynamics. And when you study physics, there are some properties which we want the physical dynamics to satisfy. So for example, you want it to be local. You don't want one atom disappears and appear there. So that's not good. And you want it to satisfy some properties like detail balance and so on. And if you study Markov chains and so on, these are the properties that guarantee that this class of dynamics are going to converge towards a Gibbs-Boltzmann distribution. So that's why we're studying the Gibbs-Boltzmann distribution. You can think as like the equilibrium limit, or when your dynamics mix, they mix towards this distribution. Of course, a very interesting question is what happens when it fails to mix and so on. But okay, we are not going to go there now. But let's say you wait exponential time. Eventually, it's going to converge to this distribution. And that's why we say we're studying equilibrium statistical physics. And some people are studying non-equilibrium statistical physics. They're studying this dynamical process. Yeah, that's a good question. Any more questions about comments, about jargon? Okay. Okay, so let me go to Cynthia's question, and then we come back to the phase transitions. That's better. So essentially, the question that we are gonna be more of a comment is that, okay, what this type of large deviation principle implies for the actual microscopic measure, so the Boltzmann-Gibbs measure over the spins. So is there a way of seeing like that, that this result implies something for the original measure that we were interested on? And the answer is yes. And actually, the full answer to this question is very subtle, but let's look at this problem specifically. So what is called the Gibbs variational principle. All right, so the claim, and that's also something you can check, is that the Boltzmann-Gibbs distribution is the unique solution to the variational problem the following variational problem. So the minimum over probability measures on the configuration space of, I'm going to define what these brackets mean, but is the average of H. H is the Hamiltonian. So the average over H over the variational measure minus 1 over beta, the Shannon entropy of the measure. And I can define this minimizer to be the free energy, which I remind you is just minus 1 over beta log of z d beta. Okay, so just to introduce the notation, so when I say this, so since I'm talking about discrete configuration space, that's just the sum over all S in the configuration space of the object that you want to take the average over mu of S. So it's just the average. Okay, so that's just a fact. You can check that this is like a convex problem on the space of measures. So you need to be careful, like if you want to define this properly. But let's be sloppy. you can check that actually if you extremize this, you find that the minimizer is exactly the Gibbs-Boltzmann measure. And this is something general. It's not something for the co-revised model, just to stress. So one thing that you can do, this is a very useful fact, because one thing that you can do, since this is the minimum, you can say, okay, sometimes it's hard to solve this problem, like to actually sample from the measure that I'm interested into, but I could try to actually extremize this over a family of distributions which I know how to sample from. So a simple family of distributions. So you have this variational problem. In theory, you have to do it over all measures, but then you say, okay, maybe what happens if I just extremize over a subset, a variational family of measures, which I know how to sample, and then this is going to be an approximation to the solution. So you can do this in general, and the idea then is the following: is that choose your favorite family of measures inside that. That's going to call a variational family. And then solve this problem for Q. So let's try one example, which is an easy example to sample. So for the, is there a question? Yeah.
Like -1, 1. Case of bodies where.
What is oh, sorry, this is a calligraphic C. So yeah, it's bad writing because it looks like a G. This is the configuration space. For the co-revised model, it's just the hypercube, -1 + 1 to the power D. But in general, this is something general. You can write for any Boltzmann-Gibbs distribution. Any Boltzmann-Gibbs distribution is going to satisfy this variational principle. So you can, in principle, write it for. Oh yeah, I should define this, yeah. And also because there is spins and entropy, so that's maybe not the best notation, but yeah, S mu is going to be the average, in this sense, of the log of, actually the minus the average of the log of mu. So that's the Shannon entropy. By the way, note how this mimics exactly the large deviation potential, right? Phi is the competition between an energy term and an entropy term. So there's beta times energy plus entropy. But that's energy and entropy in the space of summary statistics. While here is energy and entropy in the space of the measures. But this is mimicking exactly that. Like, that variational principle there for the summary statistics. Here we have a variational principle on the space of the measures. So it's kind of you can see where we are going. There was a question on the back. I don't know if. Okay, great. Yeah, thanks. Okay, so let's choose a family. I'm going to give one example, and this example is going to essentially answer Cynthia's question. The very, very basic thing that you can, a very, very basic family of distributions which is easy to sample from are the factorized distributions. So take mu of S, which is just the product measure between some, how do I call? No, I don't call mu. I call Q of SI. So I'm looking at particular examples of measures that factorize, and the family Q that I can take, which is a natural example, is the set of. So I'm going to call these mean field measures. So this is the product of 1 to D of Q of M of Si such that Q M of S is equals to 1. Sorry. So these are probabilities over the individual spins. So the probability that an individual spin is plus or minus 1 is just going to be 1 plus or minus M over 2. And it's easy to check that the average magnetization over this is exactly M. So in some sense, we are going to look at the variational problem on the family of factorized distributions which have the right magnetization when you take the average. Okay? So given this family, you can compute what is H of mu. So for the Curry-Weiss model, that's minus 1 over D sum over ij. So that's very convenient because everything is independent. Like since this is a product measure, you can just take the average inside, Si Sj over mu minus H sum over I Si of mu. And then that's essentially minus 1 over 2D. And then you have to remove the diagonal, but you just check that this is D minus 1 times M squared plus D minus H dm. So essentially this is because, let me make a comment here, this is because Si Sj equals to M squared for I different from J. And for I equals to J is just 1, right? Because these are plus or minus 1s. Sorry? So M is a parameter. It's a parameter. It's a parameter, yeah. Yeah, that's a Q sub M, yeah. So the variational principle is over measures, all measures. I'm gonna look at just a specific family, and this family is gonna be parameterized by M. And then I'm gonna be writing this minimum over mu is gonna be a minimum over M. And I don't know if you guys can anticipate, but you know, in the large deviation principle, where is my large deviation principle? Argmax over M. Okay, so now I need to compute the entropy. So I'm gonna just give you the result because I think you understood what needs to be done. So if you compute the entropy over this class of factorized measures, you're just gonna get D times S of M. So the binary entropy. Therefore, F of beta, which is the minimum over mu in Q of H minus 1 over beta S of mu is equals to the minimum over M, and M here. So M here is essentially, so this is essentially like a Bernoulli variable with probability given by parameterized by M. So you can see that M needs to be between minus 1 and 1 in order for the probability to be between 0 and 1 of this thing. minus 1 over beta Sm, where you can see from here that Em, when D is large, is exactly my energy. So that's exactly what I define there up to the beta. So the leading order term, so m squared over 2 minus this h hm. And this is exactly the variational. That's exactly the large deviation principle that I got for the revised model. So this is essentially telling me that in the high dimensional limit, my complicated high dimensional integral for the revised model is essentially a factorized measure with a given probability, factorized measure of Bernoulli's, where the Bernoulli probability is parameterized by the average magnetization of the system. The average magnetization is the solution of a one-dimensional extremization problem, which is exactly the large deviation principle that we had got in the theorem. And what is the implication then for the measure, just to be very explicit now? If I write now this family, that's essentially, I can rewrite this in the following way. E to the beta m star Si over twice the cosh of beta m star. Okay, so here there is a little bit of a jump, but I just want to show you that the implication, you can check that through this variational principle, so the extremizer of this thing, so the m star is gonna be such that I can rewrite this product measure in the following way, where m star is the solution of that. So this is very easy to sample from, because how do I sample from this? I just solve this problem. This is a one-dimensional problem. That's easy. I find m star. Once I find m star, I just need to compute, this ratio for every I, and I just sample independently, condition on m being equals to m star. So I find the average magnetization of the system, and then conditionally on the average magnetization, the system is just a product measure. So I just can sample IID conditionally on m star. So this is another way of seeing like what we call mean field, right? The system, the only thing that matters for this high dimensional measure is the average magnetization. And once I know it, the measure is just factorized. Yeah? So what I'm showing is that this assumption is exact when D is large, because the measure satisfies the same large deviation principle. So, okay, maybe I went to the argument is that, okay, I have this variation principle, I'm making an approximation, it's not exact in general, but in this case it's exact. And thank you for the question, because this reminds me that I should make a comment at this point, which is, that's not always going to be the case. So actually, most of the times is not the case. This is a very particular example that this product family is going to be exact when D is large. In many examples, actually you need a richer variational family that is to be exact in the D equals to infinity limit. So for example, in the examples that you're going to see later, you need to account for something a little bit more, like what is we call like two-body interactions. So you would need something a little bit richer than this ansatz. So this ansatz here, by the way, is what physicists call naive mean field. The naive mean field is the product measure. Then there is a little bit like of a more richer family of functions, which is, okay, it is not a product, but it is, I take into account interactions, but I take into account just two-body interactions. And that's what is going to be called the Bethe ansatz. And this is going to give us what we call the beta free energy. And then maybe the beta free energy is not good enough, then you need to put 3 body interactions. And that's what's going to be called the Kikuchi free energy, the Kikuchi family of measures, and so on. So there's a whole hierarchy of ways of constructing variational families that, you can try to match the high dimensional measure when D is large. So that's a specific case where everything is easy. And the reason everything is easy is because the Hamiltonian, so the energy function, can be written directly in terms of the magnetization, the average magnetization. And when you cannot exactly write H as an H of M, where M is the order parameter, this is not going to be the case. You need to go for a richer variational principle. And so Cynthia is going to be telling us about AMP at some point, I guess. And AMP is nothing but the simplification of something which is a little bit of a richer variational family than this one, which is what I called before the beta free energy. So AMP is going to be equivalent to actually solving a variational problem for a certain family of distributions that take into account 2 body interactions. I'm not going to go into that now, but it's just a comment so that we try to connect later with what Cynthia is going to do. Yeah.
Let me say something a little.
Yeah.
Take M star.
Yeah.
And each one independently does the burnout M star sample.
Yeah.
And then at the end, I look at the empirical average. If that is M star, I keep the sample. Otherwise, I throw it away and repeat it.
I think you can do something even simpler. I think literally what you need to do is that find M star. Once you have M star, just sample IID from a Bernoulli with that M star. That's it. And then you're good. You're going to see that all the statistical properties of this ensemble of distribution is going to be the same as the original one when D is large, sufficiently large, yeah.
So essentially what you're saying is that the original Boltzmann-Gibbs distribution is too complicated because
Yeah.
it's taking all these interactions.
Yeah.
So you're giving this nice IID distribution.
Yeah.
And this is an approximation of that. Approximation in the sense that as D goes to infinity, this to become.
Yeah. Yeah. And for finite D is actually just an approximation. And actually, if you work hard enough, you can control all the errors in this case. Actually, this example is very good because an example that you can do it fully rigorous and control every single approximation that we are making if you work hard enough. Then for more complicated problems, it becomes much more challenging. But in this case, you can do everything. If you all the mathematical questions like finite size corrections and so on, you can do for this problem.
So when you say, can you elaborate what are these calculations that you're saying? So you want to characterize the error between the Boltzmann distribution and this star product distribution. So how do you characterize that error in terms of some distance between these?
Yeah, some KL divergence between the two, and then you can see that the KL divergence has a scaling in D, and then you can do everything. You could. I mean, the calculation that I know is in KL divergence, but I guess that if you want to do in Wasserstein 2, you could also do it. Like this model is simple enough that you can do everything. Okay, so let me see how much time. Okay, so I still have 20 minutes. Let's start the discussion of phase transitions then. Yep. Just. The minimizer is not unique.
You've only found one.
So what the variational principle is telling you is that you should take the global minima first. So if there is a local minima, you should take the global minima. And my claim for this problem, and that's something that we're going to see now, is that there is one case which is not unique, the global minima, but they are going to have the same energy. So both of them are going to, you can take either of them. And actually, the measure itself is going to converge to a mixture between these two. What's going to happen, though, is that for finite D, if you actually run of them and you're going to just sample from one of them for finite D, But at infinite D, the measure actually is going to converge to like a mixture measure between 2-point masses, like peak that the M and M star and minus M star actually. We're going to see this now. But yeah, that's a good question because the whole point of this is that this measure is not log concave. So this is not going to be it's not going to be like a unique minimizer to this large deviation principle. And that's why this is interesting. Okay. There's one more. Okay. And the fact that it's not unique is going to be closely related to what physicists call phase transitions. And that's what we're going to look now. By the way, in the first lecture, we had this phase diagram of diamond with all the local minima, and we wanted to say that the system can get trapped in one of them and metastability and so on. I got a question that was that what is the x-axis and what is the y-axis? So in this problem, this is very concrete. The y-axis is this potential, and the x-axis is m. So it's the summary statistics and the free energy potential associated with this value of the summary statistics. And this is going to be key in this analysis. So, yeah.
How does the picture look? Does it just have to lower the river or does it have to?
We're gonna that's exactly where we're going. So now we're gonna study the problem of. So I'm gonna go back to the. Okay, so we want to study this problem. And what do you do when you want to find an extremizer? Well, you take the derivative and you look for the points which have zero gradient. So that's what we do. So take the derivative in m of phi, m. Okay, so that's just beta m plus beta h plus s prime of m. And then set this to be 0. And then I claim, if you just look at this guy and you take the derivative carefully of the log and everything, you can rewrite this as the following equation. M equals to 10h of beta of m plus h. So this condition is equivalent to this condition. And that thing here is what we call the mean field equation. So that's the equation that we need to solve to find extremizers. So extremizers of this potential satisfy this. This is a nonlinear, self-consistent equation because you have m in both sides, and you cannot solve it explicitly, but you can just solve it by, trying to find when a line crosses the tanh. So that's what we call, just for the jargon, we call sometimes this a self-consistent equation. Consistent. Some people will call it the mean field equations. Some people are going to call the saddle point equations for reasons which are going to become clear in next lecture. But it's the equation that you need to satisfy in the space of this potential. Okay, so now we just need to study this equation. And because this is a non-convex problem, this can have several solutions. Okay, so let's look first at a case which is simpler. So let's case zero field. So h equals to 0. So let me make a remark first about this case. is then when H equals to 0, the potential is symmetric. The symmetric function. So whenever M is a solution, minus M is also a solution. So if I have one global minima, I have two global minima if they are different from 0. So that's called a Z2 symmetry in physics. And essentially, you can see that this symmetry follows directly from the Boltzmann-Gibbs distribution, because when H equals to 0, you just have the interaction term. The interaction term is a product of two spins. So when S goes to minus S, the sign cancels. So that symmetry is a symmetry of the energy of the system. So it's logical that it translates to a symmetry of the average magnetization. So that's point 1 in my remark. The point 2 is that M star equals to 0 is always a solution. So if you look at this equation, M equals to 0 when H is 0, it's always a trivial solution. It might not be the global optima, but it is a solution to, it is an extremum. It is a critical point. Okay, so to be a bit analytical, let's look at two regimes. So at high temperatures, or beta going to 0. Well, that case is easy, right? Because the measure is the uniform measure. And so the only minimizer, like the average magnetization of the system, is 0. Because on average, there are going to be as many up and down, because just the uniform measure, like, P is just equals to the uniform measure over minus 1, 1. So the average magnetization should be 0. So actually, M star equals to 0 is the only solution of the problem. So for high temperatures, that's quite intuitive that this potential only has one maxima, and this maxima is 0. So if you plot the potential, something like is like this. Okay? What about low temperatures? So at low temperatures, when beta goes to infinity, well, when beta goes to infinity, the measure, remember, it needs to minimize the energy. And the energy is like just this SI-SJ interaction. And as we discussed in the beginning, this is actually minimized when all spins are the same, all plus 1 or minus 1. So at low temperature, we expect that, that M star equals to plus or minus 1 is also a solution. And actually, we expect this to be the global optimum, right, of this problem, because of what we know about the measure. So we might as well find that this is like the global optimum of this problem. And actually, that's easy to see there is a solution, because tan H of beta M, it's very close to the sign of M when beta is large, right? So M equals to sign of M is satisfied by plus or minus 1. So that's also consistent with what we found. Now the interesting question is what happens for intermediate temperatures, right? Like what happens when beta is not 0, not infinity, beta is something like 0.5 or 3. Okay, so, oh, by the way, it's easy to check that plus or minus 1 always has a higher value of potential than 0. So 0 is log 2. You can just check that m equals to 0, this is 0. The entropy, it's log 2. and that's exactly the entropy of the uniform measure. So everything is consistent. And you can check that plus or minus 1 is higher than log 2. So indeed, this has higher potential. So plus or minus 1 is the maximum. So what happens at intermediate beta? So I think the best way is to plot as Siva was suggesting. So what you find if you try to just solve this. So let me plot minus phi. So because it's easier to think about minimums than maximum. So minus phi, when beta is less than a certain beta critical, is just a convex thing with the minimum being 0. And then as you start to lower the temperature, what you find is that actually something like this happens. So that's minus. Of course, 0 needs to be a critical point because we showed that it's always a critical point due to the symmetry. But there are two other critical points which are at a certain value. So let's say let me not call this M star, let's call this M star the extremizer, the global one, that are at a certain value M star and minus M star, which when beta goes to infinity, gonna be plus or minus 1, but for finite beta, that can be something less than 1. So that's for beta greater than beta c. And so that's exactly what happens though. When you have like some very, very high temperature, there is only one extremizer, and this is 0. So the system essentially is dominated by the entropy. So it's like the uniform measure, the system like, there are just too many configurations. So the system is just disordered. What we call like as the disorder, the average magnetization is 0. So that's what we call a disordered, or in this case, a paramagnetic phase. And as you start lowering the temperature, at some point there is a critical temperature in which this minimum becomes a maximum and two global minimum develop. And actually the extremizer is going to be with the same probability one of the two. So the measure is going to be dominated by configurations which have with equal probability these two average magnetization. And that's what we called a ordered or ferromagnetic phase. And let's think back about the original model. We are interested in getting this magnet, putting on the stove, and heating up and seeing that at some temperature it loses magnetism. And that's exactly what is happening. Having an average magnetization which is different from 0, either plus or minus, then you start increasing the temperature or going this direction, and at some point the system becomes disordered. The system actually becomes dominated by entropy, and the average magnetization is it's 0. I'm gonna come to this. I don't think in this lecture because you just have 4 minutes. So let me make a few remarks about that and then conclude. And then next lecture, we're gonna start with the second case, which is when h is different from 0. And then I will be able to answer your question. It's something called hysteresis. But it's something that we need to have like an external field to be able to discuss that. Any more questions about these plots? Yeah. Yeah.
Then you were talking about the water level corresponding to beta and the islands, all of that.
Yeah.
We don't have that phenomenon here. So
Yeah, this problem is too simple. That's the answer to the question. So the picture I showed you, because in the first lecture, remember that we discussed different things. So first we discussed the traditional Landau-Ehrenfest point of view on phases, and that corresponds to this, is where the system actually just has two phases, ordered, disordered, and there is a transition in phase as you change one parameter, here the temperature, the system goes from one to the other, liquid, solid, or liquid vapor, if you want. So the picture I showed you where you have several local minima that corresponds to the landscape of glasses. You need a model which is, actually, the model is, let me write the model for you just for curiosity, because the model is not so much more complicated than this one, but the maths, it's, I don't know, exponentially crazier. And then you get to Talagrand and to Giorgio Parisi and the citation that I showed in the first lecture. So let me just as a side comment, just to satisfy you, consider this Hamiltonian, again, you're considering spin system, but consider a Hamiltonian that has this flavor, Jij, Si, Sj, where Si is binary, and Jij is just like a Gaussian matrix. So it's just a Gaussian matrix. And maybe I need a minus sign here. So this model is called the SK model, Sherrington-Kirkpatrick. By the way, the same Kirkpatrick of simulated annealing, the same guy, the same physicist. So quite amazing. Let's say that's the simplest model where you can get glossy behavior. And it's a very simple generalization. For our model, this was all one matrix, essentially. Now I just take it to be Gaussian, and it's crazy how easy it is to solve the model where this is all ones, and how hard it becomes once you do that. But okay, if you maybe are used to combinatorial optimization problems, you can kind of feel that this is hard. This is hard because this is not a PSD matrix. Yeah. This is a spin glass. Yeah. This is one of the many spin glasses. Yeah. And let's say that's the I think the first spin glass. If I am not mistaken, historically, that's the first model that was studied for glass behavior. Okay, so let me just make a few comments and about that, and I'm gonna finish so we can have some coffee. So comments. Maybe here take a few minutes from the break, but I'm gonna be fast. So the transition from the disordered to the ordered phase is a continuous transition in beta, in the sense that if you actually plot, if you make a GIF on your computer of varying beta in a very small grid, you're going to see that the behavior, what goes on, is that you have this minima or maxima if you're plotting phi instead of minus phi, and this maxima, is always an extremizer, is always there, and what goes on is that it goes from being like a minima to being a maxima in a continuous way. So there's no jumps, there's no discontinuity in the process as you vary beta. So that's a continuous. Also in physics jargon is what we call a second order transition. So what this means, it means that m equals to 0 goes from being a maximum of phi, which you can see this from the perspective of the self-consistent equations as being an attractor of m equals to tan h beta m, goes from being a maximum to go from being a minimum of phi a repeller of m equals to tan h beta m. And that's nice because we know that this kind of transitions, continuous transitions in dynamical systems, we can characterize them by making an expansion of phi. So you can just expand phi around m equals to 0. So that's equals to phi of 0 plus m times phi prime of 0 plus m squared over 2 phi prime prime of 0 plus order of m cubed. And if you compute carefully, what you're going to get is that you're going to get log 2. This is 0 by definition of the extremo, plus beta minus 1 over 2 of m squared plus order of m cubed. And so you can see that the Hessian of the potential changes sign when beta goes from being larger to being smaller than 1. And that's exactly the critical transition. So beta c equals to 1. That's exactly when there is a transition there, right? Because you change sign from being minima to being maximum, or for being, depends on you consider minus or plus phi. So that's nice. That's always the case. When you have a second order phase transition, which in terms of going from being an attractor to a repeller, you can always compute the critical point by making an expansion. And that's going to be corresponding to weak recovery when we do machine learning. But okay, that's just a random comment out of the blue for now. Let me give the last comment before we close. So if you look, so if you look in terms of the magnetization, the plot of m star as a function of beta, it's good to have in mind how it behaves, just because this is going to appear over and over. So that's how it behaves. So here you have a point beta c equals to 1, and then eventually this go to plus 1 or to minus 1. And yeah, so you have this bifurcation in m. So this means that if you try to find the maximum by iterating the self-consistent equations, if you are here in this region where you have this magnetization, if you start with very small m, you go up. If you start to very small negative m, you go down, right? So dynamically, if you are iterating m, you go up or down depending on the initial condition, like whether, and this is important because for finite d, so if you consider a finite d and you consider a random configuration that you initialize your dynamics, imagine like that you just sample from the uniform distribution. Well, the average is going to be 0, but the empirical average is going to be a little bit positive or a little bit negative. It's going to be 1 over square root of d, positive or negative. So if you run the dynamics, so if now you thermalize, you annihilate your system, right? You load the temperature and you let it evolve through a local dynamics, the spin are going to update, the system is going to equilibrate, and the system is going to equilibrate in one of these two configurations, equilibrium configurations, that corresponds to the one which is closest to the initial thermal fluctuation in your initial condition at finite d. So you end up to one of them depending on the initial condition. Moreover, and the reason why I'm saying that, and that's, I think, the key computational insight that you can take from this, is that since the potential is very flat at m equals to 0, right? Because the Hessian is very close to 0 when beta is close to 1, the time scale that takes for you to converge to one of the two branches close to the transition is very long, right? So if you run a physical dynamics starting close to the transition, whether you go to +1 or -1, it's going to take a lot of time, right? Because you are at this saddle point, like you're at beta equals to 1. So any algorithm that is local and is just making moves which are local in this space of the phi is going to take a very, very long time to converge to the minima close to the transition. Okay, so this has a direct computational impact on local algorithms. And that's what we call in physics critical slowing down. Okay, so critical slowing down. Which is the fact that any local algorithm that only makes small changes in the space of summary statistics are going to be very slow, close to a second order phase transition, because this space is very flat. There are d directions which are flat. So to escape them, you have to wait a lot of time in the dimension. Okay? Okay, so with this computational comment, I end today's lecture, and then we're going to see the other regime when h is larger than 0 next lecture, and then we're going to start to talk about, let's say, more machine learning problems, and see how everything that we learn here translates to the idea of like computational complexity. Okay, thank you for the attention.
Will we have